Okay, so it's a pleasure for me to introduce our speaker today at GERAD, Professor Carlile Lavor of the Unicamp University. It's in Campinas, São Paulo State, in Brazil. Carlile is a full professor there, also a researcher from the National Council of Research and Innovation, Technological Innovation. Professor Carlile was also president of the Brazilian Computation and Applied Mathematics Society from 2021 to 2024.
2018 to 2019.
Okay, 2018 to 2019, but he always in the council of the society for a long time. So for me, it's a pleasure. Carlile has a history research track in distance geometry with a book published by Springer, also acclaimed review in ASEM Computing Reviews, for which with Professor Maculin and Antonio Muscherino, they won several prizes, right? So today he will introduce us to his very new research on, from what I understood, projections in higher dimension to compute distance in the design of molecules. So Carlile, thank you for your presence today. And well, do you prefer that we make questions during the presentation? Or?
Yes, definitely. Please feel free to ask questions. Okay, absolutely no problem.
Okay, so thank you.
So thank you, Daniel, for the introduction. It's a great pleasure to be here. First time here in Montreal. And third time in Canada, as well, first time. And I'm really enjoying these beautiful colors of the autumn. So the idea of this talk is to introduce another representation of the 3D space. Maybe very new for you. And this will be a theoretical presentation, but strongly motivated by problems in computational chemistry, where efficient calculator of interatomic distances in the derivatives is very important in order to understand the 3D structure of a molecule. The traditional way to represent the 3D space is based on R3 plus and in the product. This is what we call the Euclidean representation of the 3D space. In fact, we identify the 3D space with this, but this is just one representation of the 3D space. Yeah. And the idea, as I mentioned, is to present another way to represent the 3D space. So, as I mentioned, the classical way to represent the 3D space is on the R3, and the benefits of using another representation based on R4, also plus in the product. This is very common in molecular geometry to use the so-called homogeneous coordinate to represent the 3D space. And the idea of this talk is to present the conformal model of the 3D space based on R5 plus and in the product with a little modification of the traditional one. So, and there's a joint work with Jesus Camargo and ex-PhD students, and Michael Souza from Federal University of Ceará. So in order to Daniel, where I can
not working.
Okay, here.
What do you? Você quer passar?
Yeah.
Keep it.
Maybe it's another one. It's not working. Oh,
We'll check it, Marlene. You can keep going.
Yeah. So first we have to represent atoms that we will represent as point in R3. And in order to compute interatomic distance, first we have to choose a way to represent the atoms. Okay. So instead of using the Cartesian coordinates to represent points, we can use the internal coordinates that is given by the bond length, this bond angle, and this torsion angle. So why it's good to use the internal coordinates? Because we can consider, for example, when we student proteins, we can consider that the bond lengths, and the bond angle are fixed. For example, using this toy. So here, the only degree of freedom is given by the torsion angle. Suppose that we fix the first three atoms in order to fix the reference system. So this is the first torsion angle, and this is the second torsion angle. So, and this is the degree of freedom of the molecule. So we can consider bond lengths and bond angle fixed. So using the internal coordinates, we decrease the number of the variable. Okay.
So that's how you pass through the higher dimension with this.
No. Here, 3D. Okay. So, but I mentioned, instead of using the traditional Cartesian coordinates, we use the internal coordinates.
Okay.
In fact, internal coordinates is like a local representation, because the idea is how to compute the position of this atom in terms of the three predecessors. Okay. So, and using the homogeneous coordinates in R4, that is very useful, for example, and very useful and used in computer graphics, we can represent these three movements, two rotation, and we can think about this like a translation. We can use these matrices. So we use these two matrices to represent the bond angle and the torsion angle, and look that we are in R4. And in order to represent the translation, we can use these very simple matrices. Why is nice to use the homogeneous coordinates in R4? Because in R3, it's impossible to represent translation of the 3D space using a matrix. Why? Because translation is not a linear transformation. But if we represent the 3D space in R4, we can represent translations of the 3D space using a matrix. This is why the homogeneous coordinates in R4 is nice, because we can linearize the translations. So, and if we can put everything together, we have this matrix that represent at the same time the two rotation associated to the bond angle and associated to the torsion angle, and here this is the bond length that represent the translation. So using a unique matrix, we can represent at the same time the three operations necessary to represent the atomic position. Okay, this is very, very useful in computer graphics. Yeah. So using these matrices, we can calculate the positions of all the atoms, just multiplying this matrix. So as I mentioned, we can fix this. We can fix the first atom on this position, the second atom in this position, and also the third atom in this position. Look here that the fourth coordinate is fixed. So this is the idea of the homogeneous coordinates. We can think that is very naive, because we fix all the time the fourth coordinate. But when we introduce the first torsion angle, we use before, and we just multiply the matrices, we multiply by B5 and so on. So in order to describe all the atoms, we just multiply matrices. Why? Because we are representing translations using a linear transformation. And what is precisely what is the homogeneous coordinates of a point? You can just consider the Cartesian coordinate x, y, and z, and we can put one in the fourth coordinate. This is just the homogeneous coordinates of a point in 3D space.
Can I do a stupid question?
No question is stupid. So
why it's in which applications, and in fact why it's important to know the place of an atom. Yeah.
Because as I mentioned in the beginning, our interest is to compute interatomic distance in a very efficient way. So in order to compute distances, first we have to compute the atomic position. Yeah, because for example, if we were to compute the distance between this and this, so first we have to know what is this point and where is this point. This is why it's important to calculate the atomic position. And now I'm using the homogeneous coordinates that are represented by that allow us to represent translations using matrices. So we just multiply matrices in order to compute B1, B2, and B3 are given a priori. Using B4, we compute the X4. Using B5, we compute X5, and so on. Okay? Please don't be shy. Ask the stupid question.
The size of the atom is not.
Okay. Of course, an atom can be an universe. I consider an atom just a point in the 3D space. Yeah. Our problem is to compute distances. So let's use the matrices to compute distances. So I will use this notation. Yeah, just to represent the product between matrix Bi and Bj. I use just this notation, and let's calculate the Euclidean distances. Okay. The Euclidean distance is just calculated using the norm of this difference. Yeah, this is the way that we represent the atomic position J, and the same here. So we just do this calculation, and this is the expression used in the literature to compute the interatomic distance between atom I and J. Okay, why I put this in red? Because this is not an orthogonal matrix, so we cannot remove using the orthogonality argument from the norm. But if we open this matrix, or open between aspects, if we see inside this matrix, in fact, we can use another argument, and we can prove that in fact we can represent the distance just using this expression. Yeah, this is expression using in the literature, and this is the expression that we propose to use to calculate the interatomic distance instead of this. So it's simpler. Yeah. So this is the expression when we represent the 3D space using R4, using the homogeneous coordinates. Why this expression is nice? Let's compare with the expression that we have if we represent the 3D space using R3. This is the expression. This is the expression. You see, much simpler. And why this expression is more complicated? Because here is the values associated to the bond lengths that are associated with the translations. And since in R3, we cannot linearize the translation, we have an expression like this, more complicated than this. Okay, so if we increase one dimension and represent the 3D space in R4, we can simplify the calculation of interatomic distances. Okay? But we can do more if we increase one more dimension. And this is the idea of this presentation, is to present the conformal mode or the conformal coordinates in R5. Okay. So in order to understand how to increase one more dimension, let's present the expression to calculate the position of atom X4. So we have to calculate this. And the first calculation here is the multiplication between B4 and E4 given by this expression. So as I mentioned in the beginning, this is the operator that represents at the same time 2 rotations and 1 translation. This is the rotational part of the matrix. And here is the part of the matrix related to the translation. Okay? Why I'm emphasizing this? Because this means that in order to compute the position of each atom, we have 2 rotation and 1 translation. So we have an isometry. And this is the first insight that I mentioned. I mentioned another insight. So the idea is to recognize that when we compute atomic position, in fact, we are using isometries. And we know in the 3D space and using the internal coordinates, we can represent isometries by this expression. This is a very nice exercise in analytic geometry. And of course, this is an orthogonal matrix that is associated to the rotations. And of course, because of this, this matrix is orthogonal. And this vector is associated to the translations, okay? And what we have done when we use the homogeneous coordinates, we did like this. So the meaning is that we put the translations inside the matrix. We cannot do this in R3. But since we are in R4, viewing the 3D space, we can represent the translation or at the same time, rotation, translation given by isometry. We can represent isometries in a linear way. So this is a point of the 3D space. These are the homogeneous coordinates, and we use this expression in order to compute isometries of the 3D space in a linear way. Okay? So this is an orthogonal matrix. When we put between aspa the vector B inside, and we obtain a matrix in R4, this matrix represented that responsible for the two rotation and one translations is not anymore an orthogonal matrix. So we lose the orthogonality. And one possibility, one way to present the conformal coordinates is using this idea. Is it possible to recover the orthogonality of the operator? This is a question that can guide us to the R5, okay? The answer is yes, and why I call this inside, because in fact, the conformal model of the 3D space in R5 is presented in a very different way. It's presented in the context of the Clifford algebra that is much more complicated than the basic ideas that I'm using here to present these ideas. So instead of using Clifford algebra, it's something more complicated, in order to explain what is the conformal model, we can use another way, just using basic ideas of linear algebra. And this is why I call isometry inside, because since the conformal model can orthogonalize isometries of the 3D space, so we are in the 3D space, so we represent isometries like this. And the idea, in order to explain how to obtain the conformal model, just to answer this question: is it possible to orthogonalize this matrix? Okay, so we start with an orthogonal matrix, but we have this operation that is not linearized. So we linearize when we are in R4, but we lose the orthogonality. And the question is it possible to recover? Yes, using the conformal models. So in the vector language, this is the way that we can describe the homogeneous coordinate. So we do just like this. These are the homogeneous coordinates of a point X in the 3D space. And in the conformal model, so we have another dimension. So I'm using here another notation, but I'll explain later. But this is just a change of basis. So what is important here, that we keep another dimension related to this, and we have a new dimension associated to the dimension 5. And the question is, what is this value that we can put here in order to orthogonalize isometry of the 3D space? For me, and for many colleagues that I ask the answer, when I give the answer, it's not intuitive, the answer. And the answer is this. So this is the value that we can use in the 5 dimension that orthogonalize isometries of the 3D space. So these are the homogeneous coordinates of a point in the 3D space. We generalize, because we also have the homogeneous coordinate, but we have another coordinate. And these are the conformal coordinates of a point X in the 3D space.
It's interesting because in the 4th dimension, what you add is not dependent on X and on X. And now, it is.
Yeah. This is a nice observation. When we increase from 3 to 4, no dependence, but here we have a dependence. Okay. So the next step is to explain, not using Clifford algebra, how can we obtain this? Yeah, and trying to explain this is appear the answer why we can calculate interatomic distances in a better way than the homogeneous coordinate. So first we have to represent the isometries in the conformal space. So we are using the definition of the conformal coordinates. And since A is an orthogonal matrix, we can rewrite this expression that this and using this we can obtain the associated matrix when we use the conformal coordinate, the conformal representation of a point. So these are the conformal representation of a point, and the associated matrix is this. Yeah. And since it is known that when we use the conformal representation of the 3D space, we orthogonalize, this means that this matrix, now in R5, is an orthogonal matrix. So in our particular case, because this is the answer in a general case, yeah, we are considered an isometry is given by this matrix and this vector. But in our case, just do the calculation, we obtain this nice matrix. So when we see this, we can thought that the matrix in R5 will be complicated, but no. You can see here a lot of zeros. So this is the operator now in R5 that now this matrix is orthogonal. And why is good? Why is good to be orthogonal? Yeah, because I mentioned in the beginning. In fact, we are trying to answer a mathematical question. Is it possible to recover the orthogonality? And now I'll explain why. If we work with an orthogonal matrix, why we can calculate interatomic distance, that this is our problem in an efficient way, or more efficient way. So now our problem is to explain how to obtain the conformal coordinates. And we have to answer this question. How to define a bijection between R3 and a subset of R5 in such a way that isometries in the 3D space can be represented in an orthogonal way in R5. So we have to answer this question. So the second side that you know when in mathematics is very, very important if we have a good notation. And the good notation after many tentatives is this. It looks simple, but as you know, when you give the answer, everything looks simple. Yeah? So in terms, using this notation in mathematical terms, we have to solve this implication. So answering this question is the same as find this bijection in such a way that when we have an isometry represented by F in R3, the representation will be the points that represent the 3D space will be transformed in an orthogonal way. So just the definition of orthogonal transformation using an inner product. Okay. This is the mathematical representation of this question. So our problem is how to find this that bijection in order to solve this implication. Okay. So the third insight is the following. Thinking a little bit using this implication, we can observe that if this inner product in R5 is equal to the Euclidean distance in the 3D space, you can note that the implication will be solved. So just an idea, yeah? So this idea means that we will use the inner product in R5. We will use inner product in R5 in order to calculate interatomic distance in the 3D space. This is our hypothesis. So if we consider this, so I use this square just because we have a product. So we suppose that this is valid, which means that this is also valid. And I mentioned if this hypothesis is satisfied, we answer our implication. Okay?
Why square?
Just because we are considered a product. Since we have a product, so the idea is to have a square. But you we could continue without square, and we will discover later that you have to consider square. Okay, so we will work with this hypothesis. So if we have this, our problem will be solved. Yeah, how to explain that isometries in the 3D space can be represented in an orthogonal way. So in a particular case, this is our hypothesis. So I will consider this particular case, and this is the implication. So in our particular case, we obviously have this, and we will consider that the inner product in R5 induces a NOR, obviously, and from the positivity of the inner product, we have this. Okay, very simple. But if we, because of the less implication, this is a contradiction. Why? Because I'm looking for a bijection, and this is a contradiction because we are represented all of the points in the 3D space in the point 0 in R5. So contradiction. What we do in general when we obtain a contradiction is that, okay, the hypothesis is false. Yeah. But I want this hypothesis because if I have this, our problem is solved. So instead of to consider this false, I will remove this because this is the cause of the contradiction. Removing this means that we are in R5 and we will remove the positivity of the product in R5. Why? Because it's necessary in order to keep in order to try to keep this expression valid. So it's a consequence. If we want to solve that problem, we have to, and fall in this way, you have to remove the positivity of the inner product. I will do this.
So you're still trying to find the
bijection.
And yeah, so you don't have the inner product. You just have the
yes,
what you want.
Yes. Okay. So now we are in R5 with not with a traditional inner product. We remove the positivity, but the algebraic properties we keep. So when we do calculation, is the inner product is like the traditional one. Okay. When we remove, we don't have a contradiction. We have this implication. That it seems okay. Why this implication is interesting? For two reasons. First, note that when we remove the positivity of the inner product in R5, this equation is no more trivial. Because when we have the positivity, the solution is trivial. But when we remove, it means that this equation is not trivial anymore. This is like strange, yeah? First observation. Second observation, what is the meaning of this implication? The meaning is the following. We are assuming that all of the points in the 3D space will be represented in R5 by vectors different from 0, of course, but with 0 norm. So our problem is to find a bijection between the 3D space, the R3, with a subset of R5 in order to represent in an orthogonal way the isometry of the 3D space. If you want this, these are the constants, the mathematical constants. Okay. So since we accept that the inner product is no more positivity, this is possible. Okay. So we in R5 with this different inner product means that there are vectors not equal to the 0 vectors that have 0 norm. And these are the vectors that will represent the 3D space. Okay, let's continue. So our idea is to solve this equation. So let's try to represent this in R5. So in order to try to do this, we will, and since we are trying to generalize the homogeneous model, we have the fourth dimension associated to the homogeneity, and we have the actual dimension. What is here? So this is a point of the 3D space represented using the orthogonal basis, and we assume that this new basis is an orthonormal basis of R5. We assume this, okay? And the problem is, what are the values, X4 and R5? I told you, I only remove the positivity. The algebraic properties are the same. So we have to, as I told you, we have to solve this equation. Now we have a candidate to represent the X hat. I will just use the algebraic properties and we obtain this expression. So this is the vector associated to the fourth dimension. It's like, let's say it's an Euclidean vector. So let's assume, and because as you remember, as I mentioned, I'm considering that this is orthonormal based. So the norm of this vector, the norm of this vector is 1. So this is 1. If we consider that X is different from 0, consequence, this vector must have negative norms. We remove, you accept that we remove the positivity. So it's possible to have vectors with 0 norm and also negative, also consequence, yeah? So in order to simplify, I will consider that the norm of E5 is equal to -1. Okay, let's see what's happening. Okay, fourth insight. Now I will change the basis. I'm using this basis, and this has norm equal to 1, and this has norm equal to -1. So these two vectors do not represent points in the 3D space. Why? Because we already know that if we have points in R5 that represent the 3D space, they must have 0 norm, right? So I will change the basis in order to have two vectors with 0 norm. So, and this probably is very easy to solve. There are many ways to represent this. This is a possible way, yeah. So I have E4 and E5, and I define another vectors E0 and infinity, and doing the calculation. They have 0 norm, and I put 2 here just to obtain this -1. This is also a possible solution, but in this case, the inner product between E0 and E infinity is not -1, just because of this. So this is just possibility. So we change the basis. Now we have a basis. Our basis in R5 is like this. Traditional vectors in the 3D space, 2 vectors, this norm 0, also this norm 0. Okay. So let's do the calculation. As I told you, the algebraic properties of the inner product are kept. So just doing a calculation, we obtain this. So now we have the algebraic representation of the new inner product. So these are the inner product, the new inner product between 2 points in R5, and this is the answer. So this is the traditional inner product, yeah, between points in R3, and this is the calculation that we have to do in order to satisfy all of the hypotheses that we assume. So this is our new inner product in R5 that satisfies the traditional algebraic properties, but do not respect anymore the positivity. Okay? Let's try to solve our equation. Remember that we have to obtain the solution of this equation. So using this representation, let's do this calculation. This is the answer. X0 is the coordinate of the fourth coordinate of the fourth coordinate. And this vector is associated to the homogeneous space. Our idea is to generalize. So let's consider that E0 is 1. If we consider that this 0 is 1, we solve our problem. We deduce that these are the value related to, this is the coordinate associated to the fifth dimension. So now, using just basic ideas of linear algebra, we deduce what is the value of the fifth coordinate of a point in the 3D space, avoiding the complications of the Clifford algebra.
If you have done the opposite, so
the opposite in which following?
If x infinity was equal to 1, this would implicate a different.
Yeah. But this, okay, you can do this. So you have a lot of freedom mathematics. The problem is that why you are
one of them, either of them will depend on it.
Yes. But since we are trying to generalize the homogeneous coordinates in the homogeneous space, And since in the homogeneous space, this is one, I assume this is one.
Okay.
And see and obtain the
Makes sense.
constant. Okay. Okay. So first problem is solved. How to deduce the conformal coordinates just using basic linear algebra. Now let's try to, okay. And remember that we assume that the inner product in R5 is equal to the square of the distance. And doing this calculation, we just obtain the correct value. Yeah. Okay. Now we prove when we use this, we do the calculation and we obtain, in fact, what we are looking for. The inner product, in fact, is associated to the Euclidean distance between the points. Okay. 15th side. Okay. Now, before doing the calculation, I would just try to represent. We're just trying to visualize the 3D space in R5. Visualize in R5 the. In order to do this, I will come back to the bases E4 and E5. Why? Because E4 and E5, when you use E4 and E5, we have an orthogonal basis, and this is better in order to visualize. So we will come back to the basis E4 and E5. So this is our presentation, and I know the properties that we have. Just doing the calculation, we obtain this relationship between the coordinates of the vectors. Of course, since the idea is to represent the R5, we have to represent the 3D space just using one dimension, because it's necessary to have another two if we want to see R5, okay? Yeah. And this equivalent shows that this is the equation that we want to solve. And just doing this calculation, we obtain this equation. These are just real variables. Remembering analytic geometry, what is this? So it's the equation of what? Huh?
The circle.
Hmm?
No, the triangle.
Yes.
French, at least French.
This is a cone.
Cone.
This is the equation of a cone. Yeah. So this is the equation associated to the vectors that have zero norm, which means that on the cone we have vectors with zero norm. You see, E0 and infinity are two vectors with zero norm, so they are on the cone. All the vectors on the cone, because of this, has zero norm. Here is the E1 that represents the 3D space. E4 has positive norm. All the vector inside has negative norm. So the cone is like, when you have this cone, is like you divide a space in vectors with negative norm inside on the cone. Zero norm outside the cone is the Euclidean space, the traditional space. So this is the representation that we discover using E0 and infinity. What is the meaning in using the vectorial meaning? So we start from this point, we move using the direction of E0 is here, and in the direction of infinity, we move in a parabolic way. Yeah. So this is the subset of R5 that represent the 3D space. This is the answer of our objection that we were looking for. So in order to orthogonalize isometries from the 3D space, we have to curve the space, because this is our representation of the 3D space in R5. When we do this, we orthogonalize isometries. Okay. There is many interesting things from this picture. I mentioned just one. So this vector is orthogonal to E1 and E4, okay? This vector is also orthogonal to E1 and E4. In Euclidean space, it's not possible. It's not possible. But this is not anymore an Euclidean space. Because we change the positivity of the inner product, we change the geometry, and we don't learn in our basic courses that what characterizes the Euclideanity of the space is the positivity of the inner product. When you change this, we change the geometry, and because we remove the positivity, we have a space R5 with a different geometry from the Euclidean. And I just mentioned one of the proofs that why this is not anymore in Euclidean space. Okay, so this is just for fun, let's say. So let's come back to our problem. Calculate distances. Okay. We already know that this is the algebra expression that explicitly calculate the inner product in R5. And now I will represent this using matrix form. Yeah. Just doing a calculation, we have this representation. So this is the matrix that characterize our inner product, yeah, symmetric matrix. And in a matrix language, we have this. So in order to calculate inner product in R5 that represent Euclidean distance in the 3D space, we just do this calculation. This is the conformal representation, and we just multiply using the traditional matrix language. And we just use this matrix that we call IC. IC this matrix, okay? Just using the definition of IC, we can prove this. Aha, now I explain what kind of orthogonality, but because since we change the inner product, of course, the meaning of the orthogonality is not exactly the traditional way, but these I am showing exactly in which way. So we know that an orthogonal matrix is a matrix that is a matrix such that to calculate the inverse is very easy, just to transpose. But here it's almost very easy. We just multiply at left by EC and at the right EC. So also very easy to calculate the inverse. Yeah. And this is another product. So using these two products, we can prove, in fact, that using this matrix U, when in fact this is an orthogonal matrix because when we do this calculation, we do not change the inner product. So in fact, this is an orthogonal transformation, of course, using the new inner product. But our problem is to calculate this. Now let's calculate this. So as we did in the homogeneous model, we represent our point now in R5, just multiplying matrices, exactly as the way that we did in the homogeneous model. And I use the same notation here, and I use this very nice property, yeah? Let's do the calculation. Okay, we already know that the calculation of inner product in R5 represent distances in 3D space. So let's do this calculation. We already know that in order to calculate this using matrices is just do this, okay? This is the representation of this point, the representation of this point. Now I use this property. When we transpose this, we change this. When we do this, we obtain this expression. So when we transpose this, it means that we put this matrix very close to this. And exactly at this point, we can see the benefit of the orthogonality of the matrix. Why? Because since B is an orthogonal, this disappear. The result of this is the IC. It's like our identity in R5. So all of this multiplication disappear because of the orthogonality. And note that until here, the fifth dimension, E infinity, does not appear, but IC multiplied by T0 is the infinity. And since everything here, because this is a number, I can transpose everything, we'll obtain this more beautiful expression, which means that in R5, the Euclidean distance in the 3D space is represented by this expression. Just to compare, in the homogeneous space, we have this expression, and you note here that we have to calculate the transpose here, no, and the other expression in 3D space. Note that it's like in R5, we obtain the more more intuitive in some sense. Why? Why I'm saying intuitive? Because the idea is to calculate the Euclidean distance between atom I and J. So since the idea is to calculate just the distance between I and J, we have just to multiply between I and J, and we obtain this in R5. Here, not, and here, of course, not. So you can say, okay, everything is beautiful, it's nice, but you mentioned in the beginning that the idea to increase one more dimension is to calculate Euclidean distance in a more efficient way. So the next step is, okay, calculate all of the addition and multiplication involving all of this expression. And fortunately, the conformal, this is the cost of calculation the Euclidean distance between I and J. This is the cost. If we use the conformal model, that is better than the homogeneous, that is better than the Euclidean. Of course, it's not fantastic, but it's an improvement. And for example, in molecular dynamics, when you have to calculate the energy of a molecule in all of the movement, you have to calculate interatomic distance in the billions of time in each movement. So each improvement is important. Yeah. So in addition to the fact that that this expression is much more beautiful in mathematics, you know, beauty is important. In addition to this, this expression is more efficient than the other two representation of the 3D space.
So I see that it depends on the J, the difference between J and I.
Yeah.
Why it should depend on an order of the atoms in the molecule?
No. This is just so consider that we have an ordering. 1, 2, 3, 4. Yeah, so suppose this is I and J. So the I and J. Okay. So we just subtract this and multiply by these other terms.
But why you represent it by J minus I is not only the number of atoms you have?
Yeah, so suppose that this, let's see if I understand your question. So that we have this is I and J, yeah? So first of all, in all of the three, it's important to see what is in the ordering, what is the distance between these two atoms.
Yeah, but why depends on an ordering? It's not only based on where they are in the space.
No. This is just okay. The I and J are not the Cartesian coordinates, just the position, the index of each atom, just the index.
Yeah, I didn't get something, but let's say I have something very. My question is, why is not only dependent on I and J, but also on this ordering of, maybe this is something I
okay. Yeah. Maybe okay. Why ordering is important?
Yeah, why ordering is important?
Because remember, when you want to calculate the position of one atom, you have to multiply all of the matrix BI between these two atoms. This is why ordering is important.
But you removed that.
Yes. Okay. Now, what is interesting is just the distance in terms of the order between the 2 points that we are considering.
Okay.
And this is interesting comment that I didn't think about this. Okay. I mentioned at the beginning that in computational chemistry it's important to calculate interatomic distances and their derivatives, because this is why this problem is associated to the optimization. Because when you have in a 3D space, and there is also associated a function that represents the energy, and the value of this function depends on the position of all the atoms. And if you want to understand the interaction between two molecules, you have to understand this movement, yeah. And if you want to understand the value, the 3D structure, this is associated to the global minimum of this analytic function. And this is why it's important also to calculate derivatives. Okay. So let's calculate derivatives. So first derivatives. This is the expression that we just obtained associated to the square of the distance. Yeah, this is the expression. Now we want to calculate the derivative in terms of any of the torsion angle. So the answer is just this. If we want to calculate the derivative with respect to alpha k, we just replace bk with its derivative. There is we can in fact pre-compute this. So very easy to calculate the derivative. If we use the other two representations, when you have to calculate the derivative, it's much more complicated. This is very simple. Also simple if you want to calculate second derivatives, and second derivatives using the other models, even more complicated. Here, since you have to calculate second derivative, you replace this and this associated to the torsion angle here. So exactly following the simplicity of the expression that you have to calculate the Euclidean distance. First derivative, just replace the associated measures. Second derivative, you just replace the associated measures. Okay, and these are the main references. This paper was just accepted in the last week, and thanks for your attention.
Thank you, Ricardo.